So today we are back again, but today I don't have much to say because I wasn't able to go much through group theory today. But I think we will continue yesterday's work. I don't remember yesterday's work. Let me see. So I think I will check in my history. Watch history. So where is it? I think here. No, not watch history. My videos. So yesterday. So we did yesterday. Uh, okay, we were trying to understand this permutation groups and stuff, and the representation kind of annoyed me, and we were not able to go further. And the thing is, even today it annoys me. So I don't know if I can do much even today, but let us see what we can do. Again, we are going through AZ book. It is kind of enough, I guess, easy. So let us see. I don't have any other book which just dumbs things down to this much nice level. Uh, so so we going back. So so first we will go a little more simple. We won't try to rush anything. So here we are in group theory, and this was the representation. And uh, remember that it was said that somewhere around here that I don't remember where it was written that let me see. Basically, they said that every kind of from any permutation group you have, uh, whatever element is inside it, you can always decompose it into a pair of exchanges. Uh, uh, so yeah, so here it is. This is what they are saying. Good for us. Uh, and then we go a little more. Let's see, square root identity. uh, so what exactly is a class? We have to go equivalence class. So they are saying given a group C, distinct group elements are of course not the same. Yes, that's why they are distinct. uh, but there is a sense that some group elements might be essentially the same. The notion of equivalence class makes this hunch precise. Okay, let us see what this means. uh, Before giving a formal definition, let me provide some intuitive feel for what essentially the same might mean. Uh, Consider SO3. Okay, fine. SO3 is basically in 3D group of all rotations in 3D. Uh, so uh, we feel that a rotation through 17 degree and a rotation to 71 are no way essentially the same. Uh, but in contrast, rotation 17 degree uh, z axis 17 degree x axis are essentially the same. We could simply call the x axis the z axis. As another example, uh, I don't know what he is telling. Let me just go through it. You can also read it if you are watching this. Okay, this thing confuses me sometimes. Note that at every step we manipulate the physical as to match it to tail. Okay, I think this is the takeaway from this is trying to say a group. Okay, something I don't know, something. Okay. So basically, we will just collect all the elements which mean the same thing and make a set of them. And this set, maybe we call it an equivalence class because all of them are basically the same thing. Doesn't matter which one you use how. I think that's what he's trying to say, maybe. So I will just go back a little permutation group I have studied. So let us use it. So if you have this S4 group, what does S4 group mean? Suppose you have this numbers arranged in the first, second, and third, fourth positions in such a way that you can have 1, 2, 3, 4, or you can have a 2, 3, 1, maybe 4, and so many ways. And you have 24 ways of arranging these numbers here and there inside. So basically, you have 4 factorial ways. And so here the identity will be just this one. And here suppose I want to change uh, 2 and 1, all I have to do is just to do this on this permutation array matrix, whatever we call this. And so what happens is 1 goes to 2, 2 goes to 1, and the result is something like this. So this is what happens, all this is what all happens. And the thing is, any permutation you can any permutation can be done by just repeatedly applying some combination of exchanges. And then what we have is let's see, what does A4 mean here? Why do we have an S4 and an A4? Do they mean anything different? Okay, so basically there is a subgroup we have a group A4 which is a subgroup S4. This is a group of all even permutations from S4, from 1 to 3 4. Fine. I think even permutation means just making an exchange twice. That's all that means, I think. Let's see what all we have it. So this is all, I think, the even permutations we have. First of all, we have identity, which does nothing. Let me see what 1 2 3 4 does. Let me try it. So we have, you have a 1 2 3 4, and this will be applied on this. Let's say this is what we want to apply on. First, the what 3 4 will do is it will just exchange 3 and 4. Then what 1 2 will do is it will exchange 1 and 2. That's all it will do. I don't know what is so interesting about these things. We are just exchanging, doing here and there. I just hope we get to see some real world application soon. It will be nice. Some. And so here we have. Hmm. Oh my God! So some there is some kind of permutation mathematics going on. Some permutation algebra. Uh, it is stuff I haven't seen ever before. So. So we have 12 odd permutations, 12 even permutations. Okay. I don't don't know how do we decide that what is an odd, what is an even. Hmm. It's really hard, honestly. I don't know. In an abelian world, everybody is a class by himself or herself. In any group, the identity is always proudly its own private class. Okay, so much of stuff to cover up. I don't know what to do. I can't proceed further without, understanding all the mathematics, I feel. And okay. What is a dihedral group? Okay, that's nice. Basically, it's a group about n-sided polygons. Okay. Hmm. Too much of stuff to understand. I think I can't go further. I will just I will try to continue from here itself from tomorrow. Right now, I don't have much to talk about. I mean, I didn't study much group theory today, so I want to complete it, but I can't rush it. I don't know. So, a lot of other work. I was mostly busy in condensed matter today, and so there was this nice problem. If anybody can answer, I don't know if anybody even watches this. If you have a group of finite elements, and you found out that the number of elements in this group is even, then you have to show that there exists at least one element from this G such that when you when you operate it on itself, it should give you the identity. There will always be at least one x, provided that the number of elements in uh, this group is even. And also, don't think that oh, identity. No, no, no. I am talking about non-identity elements only. Yes, there is always some at least one element which is not identity but still gives identity when it's square. If you have an even ordered group, so try it. I don't know how it works, but yeah. So I guess that's all for today. Thank you.